And welcome to our discussion on atmospheric soundings. We're going to discuss a few topics. These are introductory topics. We're going to talk about upper air observations and work our way into thermodynamic diagrams. And specifically, we're going to look at the Skew-T log P diagram. So, upper air observations are made so that we know what's going on in the atmosphere. That way we can diagnose the condition of the atmosphere. In other words, we can tell where there is high moisture, where the winds are moving a certain direction or speed. And also all that information that we take or get from the atmosphere will help us forecast what's going to happen into the future. So, when observations are made, they send up weather balloons that contain a package called a radiosonde. And these radiosondes take a profile of the atmosphere as far as the temperature and also the dew point or relative humidity. They also measure the wind direction and speed. And as they go up, they also have a pressure sensor that can tell how high they are above sea level and also the atmospheric pressure at that level. These observations are made all across the United States and all across the world. The map that you see here is a map of all the stations that are setting up radiosondes across the United States. And the standard time for radiosonde observations are at 12Z and 0Z Zulu. I think you've probably seen this before, learned this back in your introductory meteorology class. These observations are extremely important because we can take that data and then use the equations that we developed from thermodynamic theory to describe processes in the atmosphere, and we can also time step into the future to see how the atmosphere will change. In other words, forecast. So we're going to take these equations, the first law, the processes of adiabatic and diabatic heating and cooling. Also, we talked a little bit about stability and buoyancy, and from that, we can use these equations along with the data that we get for the upper atmosphere to figure out if the atmosphere is stable, unstable, and what condition it is, and how it'll change. However, using these equations are pretty hard. You need a calculator and you need really fast fingers. To make these observations and then also to calculate them takes some time. So, people back at the turn of the century, the 19th century, or actually the 20th century, came up with a way of making these calculations very quickly and very easily. They used thermodynamic diagrams. So what they did was they developed or they calculated lines on a diagram and plotted these lines to represent the processes that happen in the atmosphere. So, for example, as a parcel of air rises, it'll cool, and it cools at a certain rate, and you can calculate that. If you put that on a diagram, you can follow the air as it rises and cools. Once latent heat or once water vapor condenses, it releases latent heat, and that heating causes the parcel of air to rise at a different lapse rate or cool at a different lapse rate, and that can be calculated also. So, all of these calculations that are really difficult to make with a calculator can be done ahead of time with a calculator or other means, and can be plotted on the diagram. And then you can actually see what the parcel of air is doing as it rises or sinks through the atmosphere. So this information is plotted a long time ago, and actually what you're going to do in lab is to actually plot this data. And this is manual analysis. We actually put it on a diagram. But these days, everything is done, of course, by computer. The data is ingested by the computer, and the computer will plot it on a diagram automatically. These diagrams were first developed, as I mentioned, back in almost the turn of the 20th century. A lot of things were happening back then, in the late 1880s. The first one actually was designed by Heinrich Hertz. You probably know Hertz, not the rental car agency, but the person who invented or came up with the concept of radio waves. And he did meteorology in his spare time. It was his hobby. So he came up with something called the emagram. But other people in the 20th century came up with other concepts that are still used, or other diagrams that are used around the world, like the SkewV, or the tephigram. But in 1947, with the advent of the United States Air Force, they were born in 47 or 48, they had meteorologists and they came up with a better way. They came up with something called the Skew-T log P diagram. And this is what is used as the National Weather Service standard, and it's the most popular here in the United States. Of course, the Skew-T and all thermodynamic diagrams use 5 sets of lines. It says 4 there, that's a mistake, it's 5. And those lines that are plotted are isobars, isotherms, dry adiabats, or we also call those isentropes, also pseudo-adiabats, and then finally isoyumes. And we're going to go through what these look like on the Skew-T. And so here's a picture of the Skew-T. You've probably seen this before, but we're going to step through and look at each one of these lines, these sets of lines. First is isobars, and on the Skew-T log P diagram, isobars are horizontal, and as you go up through the atmosphere, the pressure decreases logarithmically, meaning that it decreases very rapidly at first and then more slowly in the upper levels of the atmosphere. So that's what our isobars look like, lines of constant pressure. As you go up, pressure decreases very rapidly, or decreases. Increases as you go down. And then on the Skew-T log P diagram also are isotherms, and isotherms are lines of constant temperature. If this was kind of an XY plot, then you would expect these lines to be straight up and down, in other words, vertical. But the Skew-T log P diagram skews these temperature lines, these isotherms, a little bit at a 45-degree angle to help us identify stable layers. And this is what your isotherms look like, or your lines of constant temperature. They're kind of at an angle. Also, we have processes on this chart. We're looking at the dry adiabatic process. As the air rises or sinks, it's an unsaturated process if it is not 100% relative humidity. And as a result, we can use Poisson's equation to calculate these lines of constant, actually potential temperature. You know that if you bring the air down dry adiabatically to 1,000 millibars, that's its potential temperature. So we calculate these lines, and these lines are lines of constant potential temperature. They're also the dry adiabatic lapse rate. But we're not talking about height, we're talking about pressure, so we have to use pressure to calculate these and not height. So this is what they look like, and this is what you would expect. They go off to the left as you go up through the atmosphere. In other words, temperature decreases as you go up following these lines. Each one of these lines is a line that you can follow starting at whatever temperature you're at. We also plot on the charts saturated or pseudo-adiabats, and these are lines of constant potential, equivalent potential temperature. These are for saturated adiabatic processes, meaning that if the air is saturated, it'll follow that lapse rate. And the lapse rate changes depending upon the amount of moisture in that parcel of air. Now, this is a saturated parcel. Remember that parcels that have lots of water vapor will condense lots of water and release lots of latent heat. Now, these are lines of constant potential temperature. We call this theta E. Just to refresh your memory, theta E is the potential temperature a parcel of air would have if all of its water were condensed down and that latent heat that was released warmed only the dry air. So there are your lines. You can see that they're curved. The reason for the curve is because of the varying amounts of water vapor. Where the temperatures are really warm, the air can hold lots more moisture, and as a result, the temperature doesn't decrease as much as the water vapor condenses. Where the air is really cold, it's also dry, can't hold much water, and as a result, the lapse rate looks pretty similar to the dry adiabatic lapse rate. And that's what this says. It says that after the air rises and all the moisture is wrung out, it'll be parallel pretty much to the dry adiabats. And that's what you see there. I have a plot of the dry adiabats and also the pseudo-adiabats. And where the air is drier and colder, you'll notice that it's pretty much dry adiabatic. And then the last set of lines we're going to look at are isoyumes. These are lines of constant mixing ratio. Remember, in a parcel of air, as it rises, the mass, we assume that the mass does not change, which means that the mass of water vapor stays the same and the mass of dry air. It can expand, the volume can change, temperature can change, but the mass is constant. So mixing ratio is conserved for dry adiabatic ascent. And these are lines of constant mixing ratio. So as air rises, the moisture content follows those lines. So as I mentioned before, we send up weather balloons. They measure temperature, pressure, and dew point, and we can plot these on these diagrams. Here's a plot of temperature as measured by a radiosonde. At each point, an observation was made as the balloon rose through the air. And we have this data. We can actually plot this, temperature versus pressure. And then when we connect the dots of these temperature observations, we get a line. And that is our temperature trace. We could do the same thing for dew points. It looks pretty scattered there, but as you go up, dew point varies significantly. And we can connect the dots, and we have a dew point observation. We can combine these two on one diagram, and it looks like that. This is very useful for forecasting clouds, thunderstorms, and other different types of phenomena. So we'll use this in our lab this week. That's all I have for you for this PowerPoint presentation.